Okay, so welcome to our next session on caching and prefetching. Our first two speakers, in this case, we have Rahul Bera and Zhenrong from the ETH Zurich, and they will present us Athena, synergizing data prefetching and off-chip prediction via online reinforcement learning.
Thanks, David. So, okay, let's get started then. So, hi everyone, I'm Rahul. I'm a recently graduated PhD student from Safari Research Group in ETH Zurich.
And I'm Zhenrong, currently a master's student at ETH Zurich.
And together we're going to present our work, Athena, synergizing data prefetching and off-chip prediction via online reinforcement learning. So let's get started with the executive summary. So all we know that long memory access latency significantly limit the performance of high-performance processor. And prefetching and off-chip prediction are two orthogonal techniques that has been proposed in the past to hide this memory access latency. Now, in this work, we observe we make three key observations regarding the combined usage of these two mechanisms in a system. So our first observation is that off-chip prediction and prefetching often provide complementary performance benefit. Yet, if you naively combine these two mechanisms, that often fails to realize their full performance potential together. And existing coordination policy also leave a large potential performance behind. So the goal of this work is to autonomously create a framework that can autonomously coordinate off-chip prediction with multiple data prefetchers that can provide consistent performance benefit regardless of the workload and system configuration. And to this end, we would propose Athena, whose key idea is to model this coordination as a reinforcement learning problem. Athena would work in a epoch of program execution. At the end of every epoch, Athena extracts a set of program feature from the system, for example, off-chip predictors or prefetchers accuracy, memory bandwidth usage, and use this as a state information to make a coordination action. Coordination action in this case is not only to enable or disable these two mechanisms, but also to adjust the prefetcher aggressiveness. Now, for every action, Athena also receives a numerical reward that justifies the effectiveness of taking that action. Athena uses this reward to autonomously and continuously learn the coordination policy online. Now, Athena improves upon prior learning-based mechanisms in two key ways. First, Athena introduces a composite reward framework that isolates the impact of Athena's own action than from the inherent variation in the workload behavior. And second, Athena works as prefetcher off-chip predictor coordinator as well as prefetcher control mechanism both at the same time without having any additional hardware over it. So we extensively evaluate Athena across a wide range of workloads, prefetchers, off-chip predictors, and various system design, and we show that Athena consistently outperforms multiple prior heuristic-based as well as learning-based coordination mechanisms. And all of these evaluation workloads, scripts, everything is online and fully artifact evaluated, which you can get from our GitHub repository. Okay, so with that said, so this is going to be the outline of our today's talk. So let's start with the background. So as I said, long memory access latency is and still the key performance bottleneck in modern high-performance processor. We as architects have proposed numerous techniques to address this challenge. For the scope of today's presentation, I'm going to focus on data prefetching and off-chip prediction of those two techniques. So what is data prefetching? We all know that it's a speculative technique that predicts address of future memory requests and fetches the data to the on-chip cache before the program demands them. So if your speculation is correct, then it can either partially or fully hide the memory access latency. But if the speculation goes haywire, then it can also cause memory bandwidth overhead as well as cache pollution. Now, off-chip prediction, on the other hand, is a newly proposed speculation technique that tries to identify which load requests are likely to go off-chip and start fetching the data directly from the main memory. Now, off-chip predictor, as we see, that they often provide more accurate predictions than a traditional data prefetcher, yet they offer lower timeliness than a prefetcher. So there is a dichotomy going on. So ideally, we can merge these two mechanisms orthogonally together in a system, but the question is that how do they behave in presence of each other? So that brings us to our motivation. So in this work, we are going to make three key observations. The first observation is that data prefetching and off-chip prediction provides complementary performance benefit. So what do we mean by this? So here I'm showing the performance improvement of a state-of-the-art data prefetcher Pythia employed in L2 cache in a bandwidth constrained processor that has 3.2 gigabytes of main memory bandwidth. On the x-axis, you are seeing all the workloads, y-axis is the performance numbers, so higher is better. So as you can see, in majority of the workload, even with this limited bandwidth, it improves performance. We call these workloads as prefetcher friendly, but in a good amount of workload, PTR still degrades performance, even with its inbuilt bandwidth aware throttling mechanism. But if we look into for many of those prefetcher adverse workloads, the performance improvement of a state-of-the-art off-chip predictor, it actually provides more performance benefit. Yet, if you look into Puppet's performance improvement in the prefetcher-friendly workload, it severely underperforms PTR. So it basically shows that there is a complementary performance improvement by these two mechanisms, data prefetching and off-chip prediction, that can provide. Now, what happens if we just naively combine these two? I mean, as an architect, we just simply add all of these mechanisms together, right? So here what the performance looks like. So in prefetcher adverse workloads, as I showed, that PTR degrades performance, Puppet improves performance. If you naively combine, that kind of masks out the entire benefit of what Puppet alone could have provided. Now, if we could have controlled these two mechanisms with our oracular understanding of their effectiveness, which I'm showing over here as a static-based combination of these two mechanisms, as we can see that there is a significant performance headroom than the naive combination. In the prefetcher-friendly workloads, however, PTR significantly provides better performance than Puppet, and the naive combination as well as static-based combination closely matches the PTR's performance itself. So across the board, we see that the naive combination of these two mechanisms provide a significant performance headroom than the static-based combination. So that shows that the naive combination is probably not the best solution to extract the complementary performance benefit together. So this kind of problem seems similar, right? They have. So we actually have seen multiple types of prefetchers were employed in the systems in the past. So there has been numerous solutions to control different prefetching mechanisms. However, TLP is the only mechanism that has been proposed that can combine off-chip prediction and data prefetching cleanly. Yet TLP has an Achilles heel that it can coordinate off-chip prediction with prefetchers that are only employed at the L1 data cache, not beyond that. That said, we have also extended two prior-based prefetcher coordination mechanisms, the heuristic-based HPCA and learning-based map. Both of these, by the way, are originally proposed to control only prefetchers, but in our case, we are controlling it to the off-chip predictor Puppet and PTR L2 data cache. So what we see is that in prefetcher adverse workload, it provides performance benefit, but across the board, it still has performance headroom left. So that makes us believe that there is a need for a better synergistic framework to combine these two orthogonal policies. So that's the goal of our work, that to design a holistic framework that can autonomously synergize off-chip prediction with multiple prefetchers employed throughout the cache hierarchy to deliver consistent performance benefit regardless of the underlying workloads or system configuration. And that's what Athena is. Athena formulates this coordination as a reinforcement learning problem, which now I'm passing on to Zhenrong to get you introduced.
All right. Before diving into the details of Athena, let me provide the brief basics of reinforcement learning. Reinforcement learning is an algorithmic approach to learn to take an action in a state to maximize the numerical reward. A typical RL system consists of two key components, the agent and the environment. At each time step t, the agent observes the current state, makes an action, and receives a numerical reward based on the outcome of the action. The agent's goal is to find the optimal policy that maximizes cumulative reward collected over time. The agent stores Q value for every state action pair, which represents the expected reward for taking action in a given state. For a given state, the agent selects the action that provides the highest Q value. Athena formulates a coordination of data prefetchers and off-chip predictors as a reinforcement learning problem. Athena acts as the RL agent, and the processor and memory subsystem is the environment. At every time step t, Athena observes the state, including bandwidth usage, prefetcher off-chip predictor accuracy, makes an action to enable or disable the prefetcher, and to set the prefetcher aggressiveness. At the end of each epoch, Athena receives a reward based on the outcome of its action. Now let's take a closer look into the three key components of the RL framework, starting with the state. We define the state as a vector of system-level features where each feature encapsulates a distinct behavior of the memory subsystem. Collectively, these features represent the runtime conditions relevant to making a prefetcher object prediction coordination decision. We start with these example features, such as prefetcher accuracy, object prediction accuracy, bandwidth usage, etc. Later, we perform offline feature selection using automated design space exploration to define the final subset of features that Athena uses to construct the state vector. Now, let's take a look at the action. At a high level, Athena decides whether to enable or disable the prefetcher, and at the finer granularity, adjust the aggressiveness of the prefetcher. Given a state vector, Athena looks up the Q values for each of the four actions: prefetcher only, object prediction only, both enabled, and both disabled. Athena selects the action with the highest Q value. In this example, Athena selects prefetcher only. Can we do better than solely selecting the actions at the coarse granularity? The answer is yes. We observe that the magnitude of the selected action's Q value implicitly encodes Athena's confidence in taking that action. In this case, the Q value of prefetcher only is much larger than the average of the remaining values. We exploit this observation to enable Q value-driven prefetcher aggressiveness control. The key idea is to use the Q value difference between the selected action and the average of the remaining action to control prefetcher aggressiveness. Athena does so in two steps. First, it calculates the Q value difference, delta Q. Second, using that delta Q, we drive the prefetcher aggressiveness. A low delta Q represents low confidence in the effectiveness of prefetching. Thus, Athena operates the prefetcher at low aggressiveness. On the other hand, high delta Q represents high confidence in the effectiveness of prefetching. Thus, Athena operates the prefetcher at high aggressiveness. By doing so, Athena works as a prefetcher object predictor coordinator and a prefetcher throttler at the same time using the same hardware. The reward defines the objective of Athena. Intuitively, we can use instruction committed per cycle, IPC, as the reward. However, a change in IPC may originate from two distinct sources: the coordination action taken by the agent and inherent variations in the workload behavior that are independent of the agent's action. As such, using IPC as the sole reward can be unreliable and may mislead the learned policy. To address this limitation, Athena introduces a composite reward framework. The overall reward is composed of the correlated and uncorrelated components. The correlated reward reflects the effect of Athena's action. For example, number of cycles we experience in this epoch, number of LC misses, the average LC miss latency. On the other hand, uncorrelated reward reflects inherent variations in the workload behavior that are independent of Athena's action. For example, number of load instructions in this epoch, number of mispredicted branches. This allows Athena to autonomously learn a coordination policy by isolating the true impact of its actions from inherent variations in workload behavior. We believe that this composite reward framework is potentially applicable to many other microarchitectural decision-making processes. The final configuration of Athena is summarized as follows. It includes 4 features in the state, takes an action both in the coarse and fine granularity, and the reward is composed of the correlated and uncorrelated components. In the paper, we have more details regarding the detailed design, automated design space exploration, mechanisms to measure the state, and overhead analysis. Now, let's show the evaluation results. We use ChampSim to evaluate Athena in coordinating multiple types of prefetchers of chip predictors compared against multiple prior coordination policies under a wide range of workloads and system configurations. Everything is open source and artifact evaluated with all 3 badges. We evaluate Athena using 4 different cache designs, which differ in the number of prefetchers deployed at various levels of the cache hierarchy. Let's focus on cache design 1, which employs 1 off-chip predictor in the core and 1 prefetcher at L2C. This figure demonstrates the speed up across different workload categories. On the x-axis, we have different benchmark suites, and on the y-axis, we have the geo-mean speed up over no prefetching and no off-chip prediction. Thus, higher the better. As we can see, Athena consistently outperformed prior prefetcher control policies in all workload categories. We motivated using the performance gap between existing works and static best. Do we reach our goal? The answer is yes. As we can see, in both prefetcher adverse and prefetcher friendly workloads, Athena provides similar performance gains as the static best combination. We further performed sensitivity study by varying the underlying prefetchers, and we can see Athena's performance gains is robust regardless of the underlying prefetcher. Similarly, we performed sensitivity study to vary the underlying off-chip predictor, and our results demonstrate that regardless of the underlying off-chip predictor, Athena is able to provide performance gain. We conclude that Athena provides consistent performance benefits across diverse prefetcher and off-chip predictor types. We have more evaluation results in our paper from other cache designs, performance sensitivity study, and additional results in the extended version on arXiv. Athena is completely open source along with its 100 evaluation workloads, 6 underlying prefetchers, 3 off-chip predictors, and 4 coordination policies. Now, let's conclude our presentation. We introduced Athena, which is the first reinforcement learning-based mechanism to coordinate off-chip predictor and multiple prefetchers. Athena differs from prior works in 2 major ways. First, it introduces a composite reward framework that isolates the true impact of Athena's own actions from inherent variations in workload behavior. Second, Athena works both as a prefetcher off-chip predictor coordinator and a prefetch throttler at the same time without any additional hardware. Our extensive evaluation shows that Athena provides consistent performance benefit in every configuration and workload. This concludes our presentation, and we are happy to take questions.
Time for one question. Yeah.
I'm getting mentored at university. I very much like this work, and this idea of object prediction, we've seen it being developed, and I think this is a great place, this sort of checkpoint of research in this area. This is kind of possible. There's more that you can do. What you're doing now is coordinating object prediction and prefetching. There's one more important aspect of caching and replacement. Can we coordinate these 3 things that are prefetching, object prediction, and replacement? Have you thought about that?
Yeah, so I would like to answer it in 2 parts. First, we show that Athena's performance benefit is consistent regardless of the underlying cache replacement policy. So we deployed SHIP, DDRP, and we see that Athena is able to provide consistent benefit regardless what the underlying cache replacement policy is. Second, although in our framework we did not explicitly include cache replacement in the action space, we believe that we can actually try out different cache replacement policy, get the feedback from the system, and to propose a holistic framework that addresses problem holistically. I think Athena's general framework is able to, let's say, coordinate beyond off-chip predictor and prefetchers. I hope this answers the question.
So I was wondering, your state variables probably stay the same as always, right?
Excuse me?
The state variables, how do you decide what are the features that you take?
Yes, we do offline feature selection using a held out set of testing framework.
Now, is that your training? I think we didn't show it for
Yes. So actually, we have a warm-up. We do a sensitivity on the warm-up lens to see if Athena's performance gain is consistent even if we don't warm up the RL agent. And as our evaluation sees, as we decrease the number of warm-up instructions, Athena's performance gains is consistent. And thus, we believe that Athena is able to learn quickly from the system level matrix that it collects and provide performance gain. So although we do not digest into the deep inside of Athena, we see that even if we do not warm up with zero instruction, the performance gap between Athena and prior work still persists. So this gives us a confidence that even if we have less warm up or less time to learn, Athena is able to provide performance benefit. And as other microarchitectural decision-making policies, they also need to learn their tables, right? Let's say the Tage branch predictor, etc. I don't think Athena is. Yeah, but as we demonstrate here, the performance gain is consistent.
Okay, let's thank our